In this lecture, we will look into another part of internal flow, which is regarding the flow rate and velocity measurement. So the objective is to understand various velocity and flow rate measurement techniques and learn their advantages and disadvantages. Flow rate and velocity measurement. A major applications area of fluid mechanics is the determinations of flow rate of fluids. Okay, and numerous devices have been developed over the years for the purpose of flow metering. Flow meters range widely in their level of sophistication, size, cost, accuracy, versatility, capacity, pressure drop, and operating principles. We give an overview of the meters commonly used to measure the flow rate of liquid and gases flowing through pipes and ducts. We limit our discussion to incompressible flow. Basically means the density of the liquid is constant, and therefore we can change from mass flow rate to volumetric flow rate. So this is the volumetric flow rate equals to velocity, average velocity, multiply with the area of the cross-sectional pipe or ducts. Measuring the flow rate is usually done by measuring flow velocity, and many flow meters are simply velocimeter used for the purpose of metering flow. And a primitive but fairly accurate way of measuring flow rate of water through a green hose involves collecting water in a bucket and recording the collection time. So if you want to measure the flow rate, and if you can contain the liquid by using a bucket, so you can use a bucket to contain the water, the liquid, for example. You need a stopwatch, and you need to know the volume of the bucket. So the amount of time needed to fill out the bucket will allow you to take the volume of the bucket, divide the volume of the bucket with the time, therefore it will give you the flow rate. Okay, so flow rate is simply the amount of volume that passes through the nozzles and the time that required for the volume of liquid passing through the nozzle. So that's basically how we calculate the flow rate. Okay, flow rate is volume over time. Pitot and Pitot static probes. So this is one of the measurement device that can measure the velocity. Okay, so Pitot probes, also called Pitot tube, and Pitot static probe are widely used for flow speed measurement. So in a Pitot probe is just a tube. Okay, so this is a Pitot probe. It's a tube with a pressure tab. So this is a pressure tab at stagnation point that measures stagnation pressure. So here, this point, it measures stagnation pressure. Why it has the word stagnation before pressure? So it's that the fluid, incoming fluid, is moving, right? So when the fluid reaches the tab, reaches the tip, it stops. So that's why they add the word stagnation. The fluid coming and then it stops, then it gives you the stagnation. So this is the result of this pressure is the result of stagnation of incoming fluid. That's why you call it stagnation pressure. Alright, so a Pitot tube is just a tube with a pressure tab at the stagnation point. Okay, stagnation point that measures stagnation pressure. So while a Pitot static probe has both stagnation pressure tab, okay, stagnation pressure tab, and several circumferential static pressure tab. Okay, static pressure tab. So what is the difference between this stagnation pressure and static pressure? Stagnation pressure is that the fluid, incoming fluid, has velocity, and the fluid itself has velocity, has both. I mean, the fluid itself has both velocity and static pressure. Okay, so I think easier is that I said the incoming fluid has velocity as well as pressure. So when the incoming fluid hit the tip of the what you call Pitot probe, okay, so it stops. As a result, it adds additional pressure. So originally the flowing fluid has pressure. That pressure is called static pressure. And now the velocity of the fluid is converted into pressure, so we add additional pressure into the water. So you have a total of stagnation pressure here. All right. So and then this static pressure is that the fluid is still allowed to move, but at the same time we measure the pressure of the moving fluid. So you have this called static pressure. All right. So with these two, stagnation pressure and static pressure, so this pressure is actually measured by connecting the fluid either in the middle, okay, that go down here, you measure as a stagnation pressure, and then the other pressure is you connect to another pipe. So you connect this pipe, these two pipe will be measured by a meter. So the meter will measure the pressure for different tube. So you in the end you will know the difference of pressure. So from there you will know the pressure resulted by the velocity, and then the pressure resulted from the velocity can be converted back into the velocity of the fluid. That's how we measure the velocity of the fluid. Okay, so the figure A here is a Pitot probe measures stagnation pressure at the nose of the probe. Okay, and then the Pitot static probe, this is the whole thing is a Pitot static probe, measure both stagnation pressure and static pressure, from which the flow speed is calculated. So this diagram shows the Pitot static probe. Okay, and we can actually derive the Bernoulli equation based on point 1 and point 2. Okay, point 1 and point 2. So what they do here is that we just write the Bernoulli equation for point 1 and then Bernoulli equation for point 2. Obviously both point 1 and point 2 at the same elevation, so Z1 and Z2 can be cancelled out, and then the incoming fluid at point 1 stops. So the fluid velocity here is no flow. Okay, no flow, so velocity 1 cancel. And then of course at this point 2 the water is still moving, and but at the same time you measure the pressure, so you have velocity and as well as pressure at point 2. So then we can actually simplify the equation for V2. So the V2 is the velocity of water that moving here, V2, and then you take the root square for you can simplify here. So obviously V2 will be given by P2 minus P1, right? Okay, so P1 minus P2 here. All right, and this P1 minus P2, and with the density of the liquid that flow in the system, you can estimate the velocity. So in reality, there is a meter, we call it a differential pressure transducer. So that will be the meter used to measure the pressure in the separate tube. So once the pressure is measured, they can actually calculate the pressure difference P1 minus P2, right? So if you don't want to use this static pressure, what can you do? You can also use manometer to measure the pressure. So you put a manometer tip here, somewhere here on top of the P1. Okay, so you will have this pressure in the fluid. Okay, you can measure because the manometer tube can measure the pressure in the tube. All right. So here is a close-up look into this Pitot static probe. So a close-up of a Pitot static probe showing a stagnation pressure hole. So this is a stagnation pressure hole, and 2 of the 5 static circumferential pressure hole. So you can see 2 point here. Actually there are 5. Okay, so we see 2 out of 5 static circumferential pressure holes. Okay, so the other one is called obstruction flow meter. For example, Orifice, Venturi, and nozzle meter. So here's the diagram shows a flow through a constriction in a pipe. So this is a constriction in a pipe. So originally you have a bigger diameter D, and then you constrict it down to small diameter D, small d. Okay, so from area 1 to area 2, so we have this constriction, obstruction of the flow. Alright, so flow meters based on this kind of principle are called obstruction flow meter, and are widely used to measure flow rates of gases and liquids. So it basically based on mass balance. Okay, so when you have a constant constant density, okay, we can reduce the mass flow rate to the volumetric flow rate. So the volumetric flow rate is given by A1V1 equals to A2V2. So A1V1 equals to A1V1 equals to A2V2. So so we can find the velocity at point 1 will be given by A2 over A1 multiplied with V2. So this A2 over A1 can be simplified into D over D in the bracket square, okay, multiply with V2, okay, and then we can write a Bernoulli equation for point 1 and point 2, which is given by this form. So we can see that Z1 equal to Z2, so Z1 and Z2 already cancel out, and then we can try to rearrange for velocity at point 2. Okay, we can rearrange for velocity at point 2. So what can we do? We just take this part, okay, put it here, and then equals to P1 minus P2 over rho g plus V1 square over 2g. And then we can simplify this equation further by replacing V1. Okay, so V1 will be given by this equation. So we put it here, we get something like this: d small d over big D in the bracket power 4, and then multiply with V2 square. Alright, and then we can simplify it further here, and then from here we can turn it into these forms of equation. So this is an obstruction with no loss. Okay, obstruction with no loss. How do we know there's no loss? Because we do not account for head loss here. Okay, that's why there's this equation is derived without any loss. Alright, after we get the what we call the velocity at point V2 here from this equation, which the beta is given by small d over big D. So the small d is here, the diameter, and the big D, the diameter for the bigger cross section. And then we can actually convert it into a volumetric flow rate by multiplying A2, area of this point 2, with velocity V2. So the V2 we already know, and then the A2 is actually pi small d square over 4, so it's a small diameter d. Okay, and of course just now we mentioned that there's this equation was derived without any loss. So if we want to include the minor loss as a result of this obstruction or constriction, we can include a coefficient. We call it discharge coefficient. So the losses can be accounted for by incorporating a correction factor called the discharge coefficient CD, whose value is less than 1, is determined experimentally. So if we want to find the CD value, we have to conduct experiment to determine the CD value. So this flow rate equation with this A2 and V2 will be in this form, right? But then we have additional CD as a correction factor, so we call it discharge coefficient CD. All right, so the AO is actually equals to A2, so the AO is A2 pi d square over 4. So here's the pi d square over 4, so it's A2 actually. Okay, it's A2, so we wrote that here as a naught, which but still is A2, and the beta here is small d over big D. So the value of CD, the CD depends on both these the beta and the Reynolds number. Alright, and charts and curve fit correlation CD are available for various types of obstruction meter, for example Orifice and nozzle meter. So example, this is Orifice. Just now we show the example of obstruction, constriction, those are Orifice, and then another forms of constriction we have a flow nozzle, and then the other one is venturi. So for Orifice and flow nozzle, the CD, the discharge coefficient, determined using beta as well as Reynolds number. So beta and Reynolds number. Okay, so we use equation referring to different meters. Okay, so this beta is only applicable for this equation when it's between 0.25 to 0.75, and the Reynolds number must be between 10 to the power 4 to 10 to the power 7. For flow with a Reynolds number greater than 30,000, the value of CD can be taken as 0.96 for flow nozzle and 0.61 for Orifice. So as I mentioned to you, here is the common types of obstruction meter, Orifice meter. So we have a constriction, a sharp, so we have a loss, and then flow nozzle, it doesn't have a sharp edge, and that's why it's called flow nozzle. And then we have a venturi, we have a sudden, not sudden, we have a gradual contraction and gradual expansion. The figure here show an orifice meter and a schematic showing its built-in pressure transducer and a digital readout. So basically, when you have a larger area of flow diameter, then moving to a smaller diameter, you basically have a change of pressure as well as velocity, and this will be picked up by the what we call pressure transducer. And because we have a we allow the fluid to flow up into a confined area where we place the transducer. And when the fluid flow from a bigger area to a small area, what happens is that the velocity will speed up. Okay, the velocity would speed up in a small area, but the pressure would drop. Okay, and another figure here show to you the variations of pressure along flow section with an orifice meter as measured with a piezometer tube. Okay, so we measure the pressure variations of pressure with the piezometer tubes. So we have one piezometer tube before and after the orifice meter. The loss pressure and the pressure recovery are shown. So we have a loss pressure and then a pressure recovery. So now we will look into example 8.10. Okay, it's about measuring flow rate with an orifice meter. Okay, with an orifice meter. So that the flow rate of a methanol at 20 degrees Celsius. Okay, 20 degrees Celsius, we have a density for methanol. Methanol is 788.4 kilogram over meter cube. And then we have a dynamic viscosity of methanol at 20 degrees Celsius is 5.857. Okay, 5.857 multiply 10 to the power negative 4 kilogram per second per meter per second. We have a through a 4 centimeter diameter pipe. 4 centimeter diameter pipe is to be measured with 3 centimeter diameter orifice meter. So here you have 4 centimeter and then here you have 3. Okay, so D is 4 centimeter equals to 0.04 meter, and then small d equals to 3 centimeter, which is 0.03 meter. Okay, equipped with a mercury manometer across orifice plate. So this is a manometer. Okay, so this is the whole thing. This whole thing is manometer. Okay, a different height. The different height of the manometer is 11 centimeter. So we have here 11 centimeter. So the different height here. Okay. So you are asked. Okay, so you write down the H is 11 centimeter, which is 0.11 meter. Determine the flow rate of the methanol through the pipe and the average flow velocity. So you are asked to find volumetric flow rate. Okay, what is the volumetric flow rate, and also the velocity 1. Okay, what is the velocity 1? So we're interested with the velocity through the original diameter of the pipe, which is 4 centimeter pipe. We want to know the velocity. Okay, so with this information, what can we do? We also realize that this is mercury. Mercury has a what I call okay, let's see. obviously we are given the height, which is 11 centimeter. We want to find the volumetric flow rate as well as the velocity. Okay. One thing or not, we have to use this the equation that we have to use this equation that we just derived. So we have to use this equation. Alright, so we write down this equation. So this is volumetric flow rate equals to A naught CD, and is root square of 2 multiply the pressure difference, which is rho. In this case, it is rho of mat. It's 1 minus beta to the power 4. Right? So we realize that we don't know what is the pressure difference. Okay, we can estimate the we can calculate the beta, we can guess the value of CD, we can also calculate the value of A naught. So let us begin with A naught. So A naught is basically A1 given by pi over 4 d square. Okay, so pi over 4 for big velocity, big diameter, which is 0.04 square. That should give us A naught. Let me see, A naught. Okay, we just leave it here first. So we should have this value, and then the CD we can assume it as so we are not sure about the Reynolds number, so we're not sure what kind of value we should use for the orifice. So if you really want to use the orifice, we need to know the beta as well as the Reynolds number, right? But now we don't know the Reynolds value, so we can estimate, we assume the CD value, okay, the discharge coefficient as 0.61. okay, so we assume it as 0.61. Alright, so now we have CD, and the beta is given by small d over big D. So did we calculate the small d over big D? Not yet. So the small d is 0.03, the big D is 0.04. So the value of D is 0.75. Alright, and the pressure difference, obviously we don't know, so we need to find. To find this, we need to derive an equation for this. Okay, so we have here pressure 1, here we have pressure 2. Alright, and then we have the height of the liquid. We assume this as H mat. Okay, H mat. Okay, so and then this is the height of H. Alright, and then this height should be H mat minus H. Okay, so if we are to how to say it, to find the pressure, okay, we are to find the pressure difference. We need to come up with an equation. So this equation, if we follow this line from here, P1 down, okay, here, and then we move here, and then we go up. Okay, we draw this line first, so this would guide us to derive the equation. So we start from pressure 1. Okay, then the pressure going down should be positive. Okay, so the pressure of going down should be positive, so it's plus. Okay, so we follow this line. Okay, we follow this line. Okay, I think it's not very clear if I do that. I think, yeah, we follow this line. Okay, okay, right, we follow this line. Okay, so we start with pressure P1 going down. We should have a positive pressure, which rho mat G, H is H mat. Okay, and then we move to the side, and going up will be minus rho mercury G H. Okay, then going up again, we should have minus rho mat G. This time the H is H mat minus H. Alright, that should be minus. I think we are running out of space, so I will do this. Oops. Do this. Okay. Minus. Oops. Yeah, maybe I'll make it smaller. Yeah, so I have more space. So it will be minus P2 equals to 0. So we start from P1 going down plus rho G H mat. Okay, and then going up we minus. Okay, I think I do it this way, that will be more clearer to you. Start from the top. Okay, P1 going down is plus rho G H mat. Okay, rho G H mat. Then move to the side, going up minus rho G is rho mercury rho G H. Okay, then going up again, then we have rho minus rho G, this rho mat G in the bracket H mat minus H. Okay, and now of course we have to go against the pressure at point 2, so it's minus P2. So in the end we should have equals to 0. Alright, that's how it works. So something can be cancelled out. So you see, this one and this one can be cancelled out. Okay, then we can write the equation for P1 minus P2. Okay, minus rho mgh plus rho mat g h equals to 0. So P1 minus P2 equals in the bracket rho m minus rho mat g h. Alright, so I hope it makes some sense to you in the equation. Okay, so now we have P1 minus P2. Okay, so we can use the equation already. Okay, we can use the flow rate calculation equation. So rho AO CD 2. Okay, so it's replaced with rho m rho mat GH. Okay, and then we have rho mat 1 minus beta to the power 4 bracket. So we can write rho as a pi over 4 pi over 4 0.04 square. CD we assume at 0.61. Okay, assume it as 0.61. Okay, and we have the bracket. We have the bracket 2. So for mercury is okay, so we forget about the mercury. So the mercury, the raw mercury is 13,600, okay, kilogram over meter cube. Alright, so we can put here 13,600, okay, mercury minus raw mat. Raw mat is 788.4. Right? Oh, I think we are out of space again. So this is what I will do. Okay. So we continue. G is 9.81. G is 9.81. H is you already know the H. What's the H? Is 0.11. And we have raw mat again, which is 788.4. 1 minus beta is 0.75. 0.75 to the power 4. Close the bracket. Now that's how we do it. Okay. Some space. Alright, so if we do this calculation, let me just check, make sure everything's correct. I think we make a mistake somewhere. Yeah, I think I made a mistake here. This one, A0 supposed to be A2. Okay, so this is not supposed to be big D, supposed to be small d. Alright, and then of course this value will be 0.03. Okay, 0.03. As a result, here also 0.03. Okay, 0.03. Alright. So we just move on with the calculation. If we calculate it correctly, means we use a calculator, 3.088 multiply 10 to the power -3 meter cube over second. Okay, so we can also calculate for, since we know the volumetric flow rate, we can calculate the velocity, which is volumetric flow rate over area. So our volumetric is 3.088 multiply 10 to the power -3 over pi over 4. We want to know the big diameter, so its big diameter is 0.04 square. So in this case, we should get 2.46 meter over second. Alright, 2.46 meter over second. And just now I said we guessed for the value of this, how do I call that? What's the name? CD. The CD, which is a discharge coefficient. Okay, the CD, we guess this value. Okay, we guess for the CD value. So actually, to know the CD value, we have to use this orifice meter equation. We must have this beta as well as Reynolds number, but we don't have the Reynolds number. That's why we assume the CD value. So now we have the uh, velocity, okay, and also the volumetric flow rate. So we can use the velocity to calculate the Reynolds number. So the Reynolds number given by rho methanol v1, okay, and then big D over dynamic viscosity. All right, so the rho methanol is 788.4. The V1 we already calculate here, which is the V1, and this is of course A1. The V1 is 2.46, and the big D, which is 0.04, and the mu we already know. The dynamic viscosity is given here, 5.857 multiplied 10 to the power negative 4 kilogram per meter per second. Okay, so it is 5.857 multiplied 10 to the power negative 4. Okay, so the value of the Reynolds number would be 1.32 multiplied 10 to the power 5. Alright, so with this Reynolds number, we can actually calculate the CD value. Okay, we can actually calculate the discharge coefficient value, CD value, by using this equation. Okay, by using this equation. So we shall do this now. Okay, so it's CD equals to 0.59 plus 0.0312 beta to the power 2.1 minus 0.184, okay, beta to the power 8 plus 91.71 beta, okay, 91.71 beta to the power 2.5 over Reynolds 0.75. Okay, so let us proceed. 0.5959 plus 0.0312 beta, which is the beta value, which is 0.75, 2.1 minus 1.84, 0.75 power 8 plus 91.71, 0.75, 2.5. Reynolds value would be 1.32 multiplied 10 to the power 5. Alright, 0.75. Alright, then therefore the CD value would be 0.601. Okay, 0.601. Okay, so we can use this CD value. We can we can use this CD value. We can then place it back here and then calculate for volumetric flow rate. Okay, so I have done that already using Excel. Okay, I have done that already using Excel. So we have 3.09, the first calculation, and the velocity, I mean the volumetric flow rate 3.09, 10 to the power negative 3, and then the velocity 2.46. Okay, and then we calculate the Reynolds number 1.32, 10 to the power 5, and then we calculate the CD value 0.601. So what you notice is that 0.601 is different from the value we assume. Okay, the value we assume is 0.61, but when we calculate the CD we get 0.601. So what we do, we recalculate. Okay, we use this CD value, we place it back into the flow rate equation. Okay, we place it back into the flow rate equation and calculate the flow rate again, and we get 3.04 10 to the power negative 3. Okay, so we get 3.04 10 to the power negative 3 meter cube per second. All right, and then we calculate for the flow rate. Sorry, you calculate for the from the flow rate we calculate the velocity. Okay, so we just repeat the calculation. Okay, so which calculation are we repeating? So we repeat this calculation 1, we repeat this 2 and 3 and then 4. Okay, so repeat the 1, we get 3.04 10 to the power negative 3 meter cube per second. Then we repeat calculation number 2, V1, we get, what do we get? 2.42. Okay, meter per second. And then we calculate the Reynolds number again, repeating step number 3, we get 1.30 multiply 10 to the power 5. And then we calculate step number 4 again, repeat CD value. Okay, the CD value. So the CD value we get 0.601. So one of the things we notice is that now we have this CD value and we have this CD value and this CD value. Okay, it's hard to see. We have this CD value and this CD value, it's the same. Okay, same. So what's that means? That means this value is correct. Okay, this value and this value is correct. So we have the answer. So we want to find the question is we want to find the volumetric flow rate as well as the velocity V1. So we found the volumetric flow rate as 3.04 multiply 10 to the power negative 3 meter cube per second, and then the V1 velocity is 2.42 meter per second. So that's the answer. Okay, so similarly, if you repeat here, you can also see this. So if we get this value 0.601, which is same as the CD before, so we repeat the calculation again, we still get the same answer. Okay, so if you repeat again, you will still get the same answer. All right. Okay, now we look at the positive displacement flow meter. So the total amount of mass or volume of a fluid that passes through a cross section of a pipe over a certain period of time is measured by positive displacement flow meter. So there are numerous types of displacement meter. They are based on counting, filling and discharging of the measuring chamber. So imagine that a chamber, it has a space, it has a volume, right? So the volume will be filled up by the fluid. So once the volume is filled up, it will discharge. So once it is discharged, they will count they will count that as first discharge, and then the second filling will start again. So when the second filling of the volume is fully filled, and then after it's fully filled, it will discharge again, and then this is counted as 2. So the chamber measuring the filling up and discharge number will know how much volume actually passes through the what you call the flow meter. Okay, so that's how they know in terms of time, in terms of volume. So when you have the volume and you have time, you can calculate the volumetric flow rate. Okay, so they operate by trapping a certain amount of incoming fluid, displacing it to the discharge side of the meter, and counting the number of such discharge recharge cycles to determine the total amount of fluids displaced. Okay, so here's the diagram show to you this positive displacement flow meter. Okay, and the figure below show you the internal design, and then we also have this a positive displacement flow meter with double helix 3 lobes impeller design. Okay, here show the turbine flow meter. So the figure A is an inline turbine flow meter to measure liquid flow with flow from left to right. So if you look at this figure 1, if you look at the what you call, you break it, you mean you do a cutaway view of the turbine. Then if you do a cutaway view, you can see the turbine blade inside the flow meter, and that is displayed in the figure B. All right, and those are example how they are used to measure the flow of liquid. Okay, flow of liquid in the pipe. And then the figure C is a handheld turbine flow meter to measure wind speed. Okay, so as this turbine blade spin, it can measure the wind speed, measuring no flow at the time the photo was taken. So now you can see in the figure that the blade was not moving. So at the time that this picture was taken, the blade is not moving, so that it is visible, so that you can see the turbine blades. Okay, and the flow meter in C also measure air temperature for convenience. So if you look at this turbine, it is not visible to you how they actually measure the temperature, but actually there's a small probe that appears either before or after the turbine blade, either before or after the turbine blade, that measure the air temperature. So the spinning of the blade will be counted. Okay, and the signal will be sent to this meter, and this meter can interpret the spinning of the blade and then give you the speed, and then of course the temperature is measured and also send it to this meter. So you can see here we have the 00 at the top, where it measures the wind speed, and then you can see it's 25.5. Actually this 25.5 is temperature, so it's 25.5 degrees Celsius. Okay, and then this meter, of course, sometimes they can also store the data. So sometimes this meter is not just the meter, but also the data logger. Alright. This slides shows the pedal wheel flow meter. Okay, pedal wheel flow meter is another alternative to turbine flow meter. So pedal wheel flow meter are low cost. Okay, low cost alternative to turbine flow meter for flow where very high accuracy is not required. So if you just want to measure the flow rate but not in a very high accuracy value, then pedal wheel flow meter could be an alternative because it's cheaper. The pedal wheel, the rotor and the blades is perpendicular. Okay, perpendicular to the flow rather than parallel, as was the case with turbine flow meter. Okay, so it's shown to you here. Here we have variable area flow meter, or in short we call it rotameters. It is a simple, reliable, inexpensive and easy to install flow meter with reasonably low pressure drop. Basically means low energy loss, okay, or low head loss, okay, and no electrical connections that give the direct reading of flow meter for a wide range of liquids and gases is the variable area flow meter, and also called a rotameter or float meter. So it does not require electricity, so you have to read it manually. That's why it is inexpensive, it is low cost. A variable area flow meter consists of a vertical taper conical transparent tube made of glass or plastic with a float inside that is free to move. So this what you call float. Okay, so when there's no flow, it will go to the bottom. When there's a flow, then it will move up. Okay, so where it stops, that's where you take the reading. So as fluid flow through the taper tube, the float rises. Okay, so the flow coming from the bottom going up, so this float will rise. Okay, as the flow through the taper tube, the float rises within the tube to a location where the float weights, drag force, and buoyancy force balance each other, and the net force acting on the float is 0. So when the water flowing from bottom up, this float will rise, and the place where it stopped, that's where you take the reading, and the place where it stopped is the balance between the weight of the float, the drag force, and also the buoyancy force. Okay, so the flow rate is determined by simply matching the position of the float against the graduated flow scale outside the taper transparent tube. So you see this plastic tube outside, it has a reading. So this reading where the float stop, you take the reading, and you know how fast the flow rate would be. Okay, the float itself is typically either a sphere or a loose fitting piston like cylinder. So in this case, if you see this figure A, it looks like a piston, right? Sometimes it could be a sphere as well, depending on the design. And then you see the figure A is an ordinary gravity based meter, and the figure B is a spring opposed meter. So means if the flow coming from the bottom, it has to force the spring to contract. So from this kind of contraction, we know what will be the flow rate. Okay, so a more high-tech approach in measuring flow rate would be ultrasonic flow meter. So ultrasonic flow meter operates using sound wave in the ultrasonic range, which is beyond human hearing ability, typically at the frequency of 1 megahertz. Okay, ultrasonic or acoustic flow meter operate by generating sound wave with a transducer and measuring the propagation of those waves through a flowing fluid. So there are two basic kinds of ultrasonic flow meter: transit time and Doppler effect or frequency shift flow meter. All right. So the figure here shows to you what I call the sound wave propagation. So it transmit from one place, and then it hit the wall of the pipe, and then it bounce back, and that's where you measure the what I call transmit time. Okay, transmit time, and which you can calculate the transit time. Okay, in the fluid. Okay. So apart from transit time, okay, apart from transit time flow meter, there is another one called Doppler effect. Okay, ultrasonic flow meter. So Doppler effect ultrasonic flow meter measure the average flow velocity along the sonic path. So this is a figure. Okay, so you have this what we call transmitting and also receiving element. Here you press on top of the outer surface of the pipe. There you can transmit the what you call the signal into the pipe, and then you will get the reflected signal. So that's how you determine the flow rate. Okay, so the ultrasonic, it climbs on flow meter, enables one to measure flow velocity without even contacting or disturbing the fluid by simply pressing a transducer on the outer surface of the pipe. Okay, so you just press it on the outer surface of the pipe, and then you do the measurement. The operation of a Doppler effect ultrasonic flow meter equipped with a transducer press on the outer surface of the pipe is shown here. Okay, so this is the figure showed you the transmitting element together with the receiving element. Okay, so this is a transducer that sends a signal and also receiving the signal. Okay, in the pipe is where the fluid or the liquid flows. Then we have this electromagnetic flow meter. So we have two examples: a full flow electromagnetic flow meter and also this insertion electromagnetic flow meter. So a full flow electromagnetic flow meter is a non-intrusive device that consists of a magnetic coil that encircle the pipe. So we have a magnetic coil outside of the pipe, and two electrodes drill into the pipe along the diameter flush. So there are two what I call two electrodes. Okay, drill into the pipe along the flush diameter. Okay, so so with the inner surface of the pipe, so that the electrode are in contact with the fluid but do not interfere with the flow and thus do not cause any heat loss. So the what I call the electrode drill into the pipe just in contact with the diameter and with the inner fluid, but it does not disturb the flow of the fluid. So therefore no what I call friction loss. Okay, and the other one is an insertion electromagnetic flow. Operates similarly, but the magnetic field is confined within a flow channel at the tip of a rod inserted into the flow. So you see there's a tip inserted, and then the magnetic field is actually within this flow channel. This is a very small flow channel at the tip of the rod. Okay, at the tip of the rod. Okay, at the tip of the rod. And then we have this vortex flow meter. So you place in what I call obstruction. So this obstruction you place in the middle of the pipe, and then you have a transducer at after the obstruction to measure this what I call vortices. Okay, this kind of vortices generated after the what I call obstruction. So we have this transmitting transducer as well as a receiving transducer. So this will measurement will tell us will give us the estimation of the flow rate. Okay, and here we have a thermal anemometer. Okay, or hot wire and hot furnace anemometer. Okay, so thermal anemometer involve an electrically heated sensor and utilize a thermal effect to measure flow velocity. The thermal anemometer have extremely small sensor, and thus they can be used to measure the instantaneous velocity at any point in the flow without appreciably disturbing the flow. They can measure velocities in liquid and gases accurately over a wide range, from a few centimeters to over hundreds of meters per second. So here's the diagram show to you the prop of the thermal anemometer. Okay, so thermal anemometer is called the hot wire anemometer if the sensing element is a wire. Okay, and a hot firm anemometer if the sensor is a thin metallic film. Okay, so here this figure show the electrically heated sensor and its support. So this wire support components of the hot wire prop. So these are component of the hot wire prop. Okay, the interesting about this technology is that it can measure for one dimensional, 2-dimensional, and even up to 3-dimensional velocity component simultaneously. So that's a very interesting technology. Okay, so here is another one called laser Doppler velocimetry. It is called laser Doppler velocimetry, in short LDV, also called laser velocimetry LV or laser Doppler anemometry LDA. So this is an optical technique to measure flow velocity at any desired point without disturbing the flow. Unlike thermal anemometry, LDV involves no probe or wire inserted into the flow, and thus it is a non-intrusive method. So this is a particle image velocimetry. So it is not the same as the hot wire anemometry or LDV that measure velocity at a point. This PIV provides velocity values simultaneously throughout the entire cross section, and thus it is a whole field technique. PIV combines the accuracy of LDV with the capabilities of flow visualization and provide instantaneous flow field mapping. So it's a very accurate measurement technique. This powerful PIV measurement technique, you see, it can measure the velocity at different location of a cross section. Alright, so obviously this is a hummingbird. This is a hummingbird that flows to try to get something from a tube, and as a result of the flapping of the wing, at the snapshot, they know how fast the air is actually moving. So you can see from the low velocity in blue color to the high velocity in the red color. So you can see they can estimate the air movement at a very high resolution.